David Smith here with yet one more flipped classroom math lesson. 3 tips before we start. First, you can adjust the playback speed faster or slower to suit your desire. Second, you can pause the video at any point to jot down questions or catch up with your notes. Third, you can turn on the captions so you can read my words on the screen. Today's lesson is basically an introduction to the mathematics of falling bodies. We're going to cover the essential equations and do a few problems and get you ready for a quiz that's coming in my class. Now, if you're not in my class, that doesn't matter. This should help you just fine with the mathematics of things that fall under Earth's gravity. Now, folks, in my class, we did a ruler drop experiment where we measured reaction time, and we did a falling body worksheet, which was a follow-up with lots of thinking questions about what we learned. Again, if you didn't do those activities, this video is still going to help you understand the mathematics of falling bodies. Let's get started. So before we start just using and manipulating and explaining equations, we need to describe a few things. So velocity, there's an equation for velocity, which is little v equals 32 little t. And v stands for velocity in feet per second, and t is time in seconds. So this is a way that we can find out how fast an object is falling if we know how long it has been falling. So if it's been falling for 3 seconds, we put 3 in for t, multiply it by 32, and that would be the speed in feet per seconds that the object has after 3 seconds of falling. Pretty sweet. Now, for distance, the equation is a little bit more complicated because it has a squared, but really it's not. It's still straightforward. We're still using time, but now we do it a little bit differently. So the distance an object has fallen is 16 times the time squared. Okay, so the difference between these two equations is that this one is linear, this one is quadratic. That's what the squared does. And this is in a unit exploring quadratics through modeling. So that's what we're doing. So here are my definitions of my variables in my equations, and let's take a look at a few problems. Actually, before we jump into doing some calculations, I want to show you a little bit more about the 2 kinds of relationships that we have here. Velocity is linear and distance is quadratic. So what we mean is linear equations make lines. You may have remembered that from previous studies in mathematics. So if we graph time and velocity, then if we graph all the different points along here, like maybe that's 1 second, that's 2 seconds, and so on, this is going to be a straight line. Okay, so that's our linear relationship, which is v equals 32t. Now, the distance fallen is quadratic, so it increases quadratically. So you can see that as time increases, the distance falling is increasing more and more and more. This is a curve, and this is actually a quadratic. It's 1/2 of a parabola. This would be the other half. We don't draw it because we don't do negative time, plus we don't have a situation where in reality we would generate this other limb of the parabola. But be assured that this is 1/2 of a parabola, and this is a quadratic equation, namely 16t squared. Okay, let's do some calculations around distance and using our distance calculation, and that's what we did with the reaction time experiment. So here's our equation from one of the last boards, 16t squared. This equation works for if you're using feet as your unit for distance, but we were using inches, so we converted that same equation into inches, and basically it's really simple. There's 12 inches in each foot, so we just multiplied 16 by 12, and this gives us our equation in inches. You could use either one of these to do your math, but you might need to convert to get the correct answer. So pay attention to the units in any problem that you see. Okay, so here's our first question. What is the distance fallen after 3 seconds? Now I want you to pause the video real quick, use this equation, and do the calculation, and I'm going to say inches. How many inches has it fallen? Okay. So I did my plug-in step, recommended that you always do a straight up plug-in step. Don't do anything else with the equation, but just plug in your value where your variable is. So d is going to be 192 times t, which is 3 squared. So now I'm going to do a little bit of calculating. 3 squared is 9, so d is going to be 192 times 9, which gives us 1,728 inches. Now real quick, pause the video and convert that to feet. Okay, If that's inches, I just divide by 12 to get feet, and we get 144 feet. All right, now that we've used time to find distance, we can go the other way. So if you know how far an object has fallen, you can calculate the time that it has been falling. So the easiest way to do that is to rearrange this equation to make a custom equation that solves for distance. So to do that, we need to get t alone. So the first thing I'm going to do is I'm going to divide both sides by 192. And that's going to give me, and I'm going to switch sides just because I like my variable to be on the left side. T squared equals d over 192. Now if t's not alone, it's squared, so we have to take the square root of both sides, and I'm going to get t equals square root of d over 192. So this means if I know the distance that an object has fallen, I can use this equation to calculate how long it's been falling. So I'm going to say, do this. What if the distance is 120 inches? Pause the video and figure out how long that object has been falling. Okay, so here's my plug-in step. I just put in my 120 inches in there for distance in my equation, and then I took 120 divided by 192, that gets me 0.625. Square root of 0.625 is 0.0791 seconds. So an object falls 120 inches before 1 second has passed. That's pretty far. Okay, after we did some distance calculations, what we did is we took a look at how changes in time affect changes in distance. So we did a little table like this where I'm using this equation, so all my units are in inches, and I recorded the time spent falling and the distance it's fallen. So the first two rows of this table are just after 1 second, it's fallen 192. That's just putting 1 in there. After 2 seconds, it's fallen 768 inches. 4 seconds here, and then 8 seconds here. And you can see I'm just doubling as I go because that makes the pattern super obvious. Now check this out. What I've done is I've multiplied my time by 2 here. 1 times 2 gives me 2. Here I've multiplied my time by 4. And here I've multiplied by time by 8. So these are my multipliers for time. Now I want you to pause the video and think real hard. What ends up being the multiplier for distance? We've multiplied the time by these numbers. What has been the multiplier for distance? Okay, so I just divided my new distance by my old distance to find out how many times it was increased by. And so when we multiplied time by 2, we multiplied distance by 4. We multiplied time by 4, we multiplied distance by 16, and then finally by 8 gave us by 64. So, okay, I made a quick change over here, and let's discuss this prompt. Use the time multiplier to express the distance multiplier in these 3 things. So here's our time multiplier. Now we can express the distance multiplier in terms of these numbers. Pause the video real quick and do that. Okay. So check this out. When we multiply time by some number, distance is multiplied by that number squared. Okay? So in a fundamental sense, distance is related to time as its square. Or another way to put this, and I was prompting you guys in class to come up with one sentence that explains this relationship, and that sentence would be, distance increases with the square of time. So think about that, write it down. Distance increases with the square of time. Okay, let's do a similar discussion about velocity as a function of time. So you had this equation, v equals 32t, and this was for velocity expressed in feet per second. If we want to convert it to inches per second, we would just multiply 32 by 12 and get 384 inches. Okay, so 2 equations. Pay attention to the units that are asked for or expressed in the problem. Okay, and just remember, every foot has 12 inches. Okay, so here's the question. Some object falls for 4 seconds. What is its velocity? Pause the video and do that calculation and come right back. Okay, here's my straight up plug-in step, my velocity equation. Velocity is 32. times the time in seconds. So I put 4 in there, did my math, and I got 128 feet per second. So that's how fast the object is falling after 4 seconds. And if I was prompted to do it in inches, I could do my conversion now by multiplying by 12, because there's 12 inches in every foot, and get 1536 inches per second. But for velocity, inches per second is like almost never used. You want to stay in feet per second. So just like with distance and time, we can use velocity and time the other way. So if you know the velocity or the speed an object is falling, you can calculate how long it has been falling. So check this out. Here's our question. The object is falling at 276 feet per second. So that's its speed or its velocity. How long has it been falling? So you're going to need to rearrange this equation to solve for time. So go ahead, pause the video and do that. Okay, so here's my equation. Velocity equals 32t. To get the t alone, I just divided both sides by 32. I brought my t over to this side because that's how we like to express these things. So the time is just the velocity divided by 32. So now that you have an equation to find time if you know velocity, go ahead and plug in your numbers from our situation here and solve for time. Okay, so here's what I get. I plugged in my velocity, 276 feet per second divided by 32, and I get 8.26 seconds. So in this case, that's how long the object has been falling in order to achieve this velocity. Okay, quickly here, we are going to analyze the multipliers for velocity and for time. So just like we did it with distance, we're going to take, here's our first number. We don't have a multiplier yet. When the time is 1 second, the velocity is 32 feet per second. And when the time is 2 seconds, velocity is 64, 3, 96, 4, 128. So this is what happens to velocity as you go from 1 to 2 to 3 to 4 seconds. Okay, so our time multiplier is just the same as the amount of seconds. So we multiplied this by 2, we multiplied this by 3, we multiplied it by 4. So the time multiplier, we're just multiplying that first time by 2, 3, and 4. So there's our multipliers. Now, I want you to figure out what is the velocity multipliers. Put those in these 3 spots. Pause the video and think real hard, do that. Okay, so check this out. The velocity multiplier is the same as the time multiplier. We had a velocity of 32. When we multiplied time by 2 to get 2 and 64 for velocity, we also multiplied the old velocity by 2 to get 64. Same with 3 seconds. We multiplied this velocity by 3 to get to 96. So that's our velocity multiplier. And then finally, when we had 4 seconds, our time multiplier was 4. And we also multiplied 32 by 4 to get 4 for our velocity multiplier. Okay, let's move into a modeling type of a problem, which are word problems. And you've seen some of these in my class. And even if you're not in my class, undoubtedly you've seen problems like this one. So we have an object that's dropped off of a 76 foot high cliff. First prompt, write an equation for the height above the ground. Pause the video and come back. Okay, so the way these equations work is you put the starting height first, and then you subtract a distance for every second that it's fallen. So remember, this part here, 16t squared, is the distance fallen. So what we're doing is we're starting at 576 and we're subtracting this term depending on the number of seconds from our original height to calculate the height above the ground. So that's our equation. Second prompt, find the height after 2.3 seconds. Pause the video, then come back. All right, I did my plug-in step. I put in 2.3 right here for t, brought everything else down. So there's my plug-in step. Then I pulled out my trusty calculator, I crunched the numbers, and I got 491.36 feet. So after 2.3 seconds of falling, that's how high above the ground this object is. Okay, so now we have 2 more prompts for this scenario. Remember, object is dropped from a 576 foot high cliff. Part C, when does it hit the ground? Now this requires a critical thinking step before you can do your algebra. So pause the video, do that step, do your algebra, come back when you have an answer. Okay, here's what I did. I just set the height equal to 0. That is the trick for this one. When it hits the ground, the height is 0. So this is our height above ground equation. So we just set it equal to 0. We manipulate it around. So I subtracted 16t squared and moved it over here. So now all my terms are positive. That makes things easier. Now I need to get t alone. The first step is divide through by 16. I divided both sides by 16. That leaves me with 576 over 16. Then I finally take the square root of t to get that alone, and that would be the square root of 576 over t, which is that. Let me pull out my calculator, and this ends up being exactly 6 seconds. 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 All right, last question. How fast is the object going the instant it hits the ground? And there's even a little more critical thinking here to be able to set this up to do the basic algebra you need to answer this question. So pause the video, play with some things, write some stuff down, and then come back. Okay, the first thing to realize is that we found out from the last prompt that it hits the ground at 6 seconds. So now we have an equation for velocity. Velocity equals 32t. So now do your plug-in step and solve that equation and come back when you find your velocity. Okay, so our velocity is 192 feet per second, the instant it hits the ground. Now, you can't take the easy way out and say, oh, when it hits the ground, it's not moving anymore. That's the instant after it hits the ground. The instant it hits the ground is right before, and it's still moving quite quickly. So don't dodge this question and say, oh, it's not going at all. It's 0. Now that you've watched the video, take a moment to jot down extra notes or jot down some questions for our next class. You can also re-watch portions of the video that you didn't get the first time. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.